All right, hello. My name is Cameron Kirk, and welcome back to my tutorial series on programming the DE10 Nano FPGA. Today I wanted to try to cover how to use K-maps, which is a method for taking a set of inputs and sort of encoding a particular output for a given set of inputs. So what I'm trying to say is you're going to take the inputs, so however many control signals you have. So these might be your little switches, these might be push buttons, these might be sensors. They can give a logical 0 or logical 1. But these are your input signals, and you know what you want on the output. So you have maybe an alarm system. That's an example I really like to go back to. Is you think of each door being an input to your system, and ultimately your output is going to be sound the alarm 1 or don't sound the alarm 0. Now that doesn't quite work in the example of K-maps, because K-maps let you do something a little bit more intricate than that. The security system is like a super simple case. Obviously, if any of the signals are a 1, you want to sound the alarm. But what happens if you want to just sort of like, okay, if I have this particular situation, I want to trigger an alert. And if I have these particular situations, I want to be 0. And you can also even incorporate don't cares and say, I don't care what happens if I'm in this particular signal. So in this example video, I am not going to be making a real world example. I'm just going to make it totally made up. I'm just going to punch in random numbers and kind of close my eyes and do it. But then what we're going to do is we're going to derive our equation. And that's another thing. So the K-map method, this allows you to sort of make it easier to just sort of like find what your equation is going to be. So instead of like thinking really hard every single time, like, okay, I need to have this logical gate here, and thinking through the logic and building the logic yourself to like place your blocks and create a circuit that's going to do what you want. This is a systematic way of you punch in what you want to have happen, giving these different cases, and you just sort of have your logic equation just sort of fall out of it in a very nice way, in a very systematic way, and it requires no thinking on your behalf. You just have to follow the process. So that is a pretty powerful tool, especially as you start to get bigger and bigger systems. It's very, very nice to to have a systematic way of deriving an equation, a Boolean algebra equation that is going to tell you what logic gates you need to use for your combinational logic. So it's pretty powerful. You have a method of telling it what you want, and then it tells you the logic required to make that happen. And it's pretty cool stuff. So let's jump right in. Let me see here. Minimize this. And then let me switch over to this camera. I'm trying out something new, trying out some shortcuts for changing the scene. And I just want to make sure this is working. Yes, this is working. Okay, good. So you should see Excel right now, and I can see that you can see Excel, so this did work. So the reason why I'm in Excel is I think this is a great, let me make sure I am recording. Okay, good, I'm recording. I think this is a great way to make truth tables. So let me just show you quickly. And also it's easy to read and follow along. You don't have to read my messy handwriting or anything like that. So here are my inputs. I'm going to have A, B, and C as my inputs. So again, this could be switch 0, this could be switch 1, this could be switch 2. And if the switches are in a certain configuration, I want something to happen. I want to send a 1 on my output. In this case, I'm going to keep it real simple, and we're only going to have one output signal. But if we wanted multiple output signals and we wanted to encode multiple output signals, we can absolutely do that. We might see that in a later example. Depending on how long this video takes, it might be in another video where we see more advanced examples of like just how powerful this method is. So for now, we're just doing a single output. And by the way, feel free to do your own homework, your own research, do a little bit of Googling. YouTube has loads of great tutorials that show you how to use K-maps. And then the purpose of my tutorial is to give you one quick short example of a K-map so you get a taste for how powerful it is. Then I'm going to show you how you take that and you turn it into, we're going to do a block diagram this video, so we're going to be working with the pictures, we're going to drag and drop our logic gates and put it together. Program the board, we'll do the waveform, and we'll actually program the board, and then we'll verify the design. Okay, enough talking, let's start doing. So the fastest way that I think to draw a truth table is to come over here and put a 0, 1, and then we'll copy and paste that. And then we'll do a 0, we'll do a 0, we'll do a 1, we'll do a 1. Great. And then we'll copy these guys, that whole block, put it underneath. And then we'll do a 0, 0, 0, 0. Too many zeros. We need a 1 here. 1, 1. And that is every single possible combination. Yeah, I'm just kind of skimming through, making sure I did that right. Yeah, I did. Okay, cool. So now I'm going to close my eyes and I'm going to say, maybe this one is important to me. This is not cooked up beforehand. I really am just kind of blindly making this up. Let's make that guy a 0. Let's make this one a 1. Let's make this one a 1. Let's make this one a 1. Let's make that one a 0. I don't know. Better yet, let's make that one a 1. Let's make these guys zeros. Okay, who knows, right? And I'm gonna go ahead and give that table an outline. So let's give it all outside borders. Actually, I think we want all borders. I don't think it really matters though. All borders, cool. All right, so here's how we're gonna do our K-map. Okay. It's a little bit easier to draw out, but basically what we want is we want a box, and we want this box to be 2 rows and 4 columns. So basically like that. We draw all borders here. And over here, this guy is going to be our variable C. So when C is true, this guy will be when C is true. And to denote when C is 0, I'm going to do C apostrophe. That'll be my C naught. Okay? So when C is 0, you can call it C naught, or the negation of C. And when you have C is true, you just put C. Okay? And so that's going to be, so this row is when we have C naught, or C is equal to 0. And this row is when C is equal to 1. And then up here, we're going to put A and B together. So we're going to have not A, not B. So when A is 0 and B is 0. And then here's the trick with K-maps. Now we're going to have when A is 0 and we have B. And then as you kind of iterate through and you have 2 variables grouped together, you can only make a change of 1 bit at a time. So B is going to stay the same, and we're going to change A. And now we have A is true and B is true. And then our missing one here is when A is true and B is not true. And so this can be, 0, 0. Oops, we can't get 2 decimal zeros. Let's do 0, 0. And then we have 0, 1. And then we have 1, 1. And then we have 1, 0. Okay, so we did not count up in binary going across here. If we counted up, it would be 0, 0, 0, 1, 1, 0, and 1, 1. But for K-maps, the trick is as you move across here and you have 2 variables together, only 1 bit can change in between these fields. So we are starting out at 0 and this bit changes. And then if we were to go to this guy next, you notice that this bit changes, the B bit changes to 0, and the A bit changes to 1. And that's not going to work for us. That's why we need to go to 1, 1 next, or we need to go to A, B next. So we go from A naught B to A, B. All right. That's a little small tricky thing it's something that I forgot earlier when I first started trying to do a K-map for the first time in years. And then over here we have C naught, which is 0, and C, which is 1 when C is 1. Cool. So now we can start to fill out this K-map. We have this grid here, and the way this is going to get filled out is really what we want is we want to look at, okay, when we have the case of A0, B0, C0, that is this guy up here. What we want is this to be equal to this guy. And actually, I kind of like using the equal sign. And then when we have 0, 0, 1, so C is 1, so 0, 0, 1, and we want it to be equal to that guy. So as you can see, we're kind of filling things out here. Now next up we have 0, 1, 0, 0, 1, 0. We want it equal to this guy. So equal to this guy. Great. And of course this guy is the next one. So there he is. Yep, so far so good. This guy is the next one, 1, 1, 0. 1, 1, 0 is down here. 1, 1, 0 is down here. So there he is. And 1, 1, 1 is right there. 1, 1, 1 is right there. And we have 1, 0, 0. So 1, 0, 0 is right there. There he is. And 1, 0, 1, 1, 1, 1, 0, 1 is right there. Okay, so this is where I kind of like to do these on paper instead, because what I like to do next, or what you're supposed to do next, is you want to draw a circle around groups of ones. And the rules are, if you're going to make a group, it can contain either 1, 1, 2 ones. If you want to group them together, you need 2 ones. If you want to make a bigger group, you have to have 4 ones all next to each other. They have to be in cells right next to each other. And then next up is going to be 8 ones. And if you're not sure what this is, and then after that you need 16 ones, but I don't think you'll ever get up to 16 ones. That's kind of a big K-map, and that would be kind of difficult to work with. But these are powers of 2. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. So we're counting it, or we're counting in powers of 2 for groupings. So let me just kind of, we'll just get these off our screen. All right, so right away, one other thing that can happen is, no, let's just do this. So I see a group of 4 right there, and I'm going to highlight it in, let's do green. And then I see a group of 1 by itself, which is fine. That's fine. We'll do that guy in blue. So, and we're done. Yeah. Now, one thing that's kind of interesting is, let's say you have a 1 here. Like here, let's just copy this whole, let's copy this table. I want to copy just the values. Paste, and we're going to paste just the values. Okay, so now we have a copy of this table. Let's say we have a table like this. All right, so we can make, well, we have one guy by himself, one guy by himself. But these guys can be grouped together. And again, this is why it's kind of nice to draw, because the tables kind of like wrap around. So like, it's kind of like Pac-Man. Like as you start coming to the end of your screen, and then if you try to walk off the screen, you try to walk off of this map, it actually loops around and brings you into here. So these kind of like loop around. So if you want to go to the cell to the right of this one, you pop over here and you're in this one. And so technically these guys, the wall of this guy is touching the wall of this guy, and you can actually make a circle and group these guys together. It's the same thing for top and bottom. This wall here is connected to this wall here. And so, if we had a more complicated K-map here on a bigger grid, and there were more numbers separating these guys, they could connect by going around the other side. It's easier to see if you draw it out on paper, It's a little bit harder to illustrate that on Excel, but yeah, I just wanted to point that out. Don't worry about it right now. Cool. So now what we need to do is we have our groups, and what these groups represent is they are representing the minterms of our equation. So what a minterm, let me write that out, minterm. Oh, I did it in caps, but that's okay. So maybe in one of your math classes, you've seen an equation something like this. And when you see A next to B, you know that they mean A times B. If two things are next to each other, it's A times B. Additionally, C times D, and then you add them together. You do order of operation. But we're dealing with Boolean algebra here. And so instead of multiplication, it's actually going to be the logical AND gate. So we're going to do A, and B. When they're sitting next to each other like that, it means A and B. And C and D when they're sitting next to each other like that. That's in Boolean algebra. And additionally, when you have a term that is just signals that are being ANDed together, and you can have many, so maybe we have A, B, E, G. Those are all just sitting next to each other, and then we have like plus D. A, B, E, G is a minterm. So those are all the ones being ANDed together. And then D is a minterm as well. And then they're both being ORed together. Oh, that's the other thing. So the plus represents an OR. So you would read this as A and B or C and D. So the groupings here are going to give us a minterm, which is all the things we need to do a logical AND together. Okay, so each group represents one minterm. So that group is a minterm. Okay, so now we've done all this work. Let's take this green group here and let's try to pull out the minterm. And the way we're going to do this is we can see, if we just look at the columns here, our y is 1 when a is 0, but our y is 1 when the a is 1. So it's clear to me that y is going to be 1 whether or not a is on or off. Yeah, because we have not a and a. So it's clear to me that y does not seem to care a. It is not following along with a. A is a control signal. It's signaling, hey, I'm 0 now. Y is a 1. Now a is like, hey, listen to me, I'm a 1. Y is not changing. It's not budging. It really isn't listening to this a at all. So that means that we can ignore it from our first minterm here. Y isn't listening, so y is not going to follow a. Now, if we look at B, B is a 1, y is a 1. B is still a 1, y is a 1. So y is listening to B. If we have a B that is a 1, we can say y will be a 1. Okay? And then additionally, when C is a 0, y doesn't listen. When C is a 1, y doesn't listen. So B is going to be our only guy here for this grouping. Okay. Next up, now this is a special case. Y is a 1 when we have this particular sequence, A1, B0, C1. So our other minterm is going to be A, B0, and C. And then we need to OR these guys together. OR. Now, if I did this correctly, we have B plus A, B0, C. This is our logic that is going to give us this sort of behavior, this sort of output. Now let's kind of go through and do a check and see if this is true. So if we ever have a 1 on a B, we're going to have a 1 on the Y. So 1 on the B, 1 on the Y, 1 on the B, 1 on the Y. And then it's saying if we ever have not B, so that's these guys. Let's go ahead and color code this. We're going to say, oh, not B here. there is still one case where we do get a 1, even though B is a not B. So we have not B, and we have A is true. So that's going to be in this section, somewhere in here. A is true. And we need to have C is true. So the only time C is true is right there and right there. And the only time we have all of it is going to be on this particular case. So we see that our logic, this equation right here, has just fallen out of the K-map, and it has told us what logic gates we need to use to make this sort of behavior happen. And it all started with the truth table. Obviously, this part of the truth table, the A, B, C, these are your inputs. And as a matter of fact, let me just put a label on there. Inputs. Boom, boom, boom. Merge. Where's the merge? Merge and center. And this is your output. Yeah, let's make that big text. Excellent. Inputs, outputs. So we want every single possible combination of inputs, and then we get to make up for our special situation what kind of behavior we want our LED light to do. So basically we're gonna say like, hey, I have special cases in here. These signals mean something to me, and when this one's doing this one, that one's doing that one, I want it to be true, and I'm too lazy to figure out the logic myself. I want a systematic way of deriving that equation, which is the K-map. K-map. Excellent. So feel free to look at more examples around on the internet, do your own homework. I might do another example using K-maps in the future. I haven't decided yet, but this is a very powerful tool and sort of like a building block as we start doing more and more advanced logical circuits. So with that out of the way, I think we are at a good place where we can switch over to Quartus Prime. And hold on, let me switch over to this camera for a second. Oh yeah, we're doing good. Okay, I'm just paranoid. I didn't actually switch scenes. Okay, excellent. So let's make a new project. New project. No, not a new. We're gonna close this project. I am recording, right? I know I keep saying that. Okay, new project wizard. Oh yeah, and if you don't remember how to make a new project, we're gonna use the handy dandy oh, it's in my DE10 folder, that's why I can't find it. DE10 nano, and my first FPGA write-up, and the repos, and the Terrasec DE10 nano kit tutorials, my first FPGA. In previous videos I show you how you can get access to this PDF, but I will also show it on screen. Okay, this guy kind of shows you the process of setting up a project, and there is some information we're gonna have to pull out of here, but I'm gonna do it myself until I hit a roadblock, and we will look at the PDF for the answer. So we'll click next. We need a folder. This will be live demos. Oh, are we in vid 4? Did I say it was vid 3? My bad. Video 4. My gosh, where's the time going? We're working at a vid 4 folder. Let's call this K-map demo. Nice. Click next. And I mention this every time, but once you pick a name for this project, that is going to be the name of your top level design entity, and you need to keep consistent, and you need to actually have a design file in your project that matches this name. So if you, this is kind of new. I actually haven't seen this in Quartus Prime, but they let you change the top level design entity in a nice convenient way in the wizard. But yeah, once you assign this, you need to stay consistent, otherwise you're gonna get compilation errors. So just keep it all matchy if you don't want to fuss with it too much. Okay, click next, create an empty project, click next. We're not adding any starter files. Okay, this is where I might need some help. I believe we're doing device, and it's SE base. SE base. I'm going to try and do this, and then I'll check if I'm right, because I'd love to have this memorized. This is the 23 I7 23. I think it's that guy. Okay, let's see if I'm right. Bam, bam, bam. All right, SE base CSE BA6U23I7. CSE BA6U23I7 SE base. I got it right. Okay, cool. Next. We're not using any custom tools. We're using the default, and finish. Awesome. I'm excited. I am excited for this one. So we're going to hook up our output to the LED, and we're going to hook up our inputs to flip switches on the board. So switch 0, switch 1, switch 2. Okay, so we're going to stick with the block diagram for now. We're not going to introduce any Verilog yet. So look for, so I went up to File, I went to New, and I went to Block Diagram, Schematic File, click OK. All right, here we are. And now let's switch over to Excel and look at our equation. And we're saying A plus B naught, we have B and then, okay, so let's do this. Let's get our inputs and our outputs on there. So let's go back, Control-Shift-2. And, okay, so we're gonna come up here at the top and then click right up here and do an input. We're gonna put down 3 inputs. Boom, boom, boom. Let's zoom in a little bit. This isn't gonna be too big of a design. There we go. And we need an output. Where's our output? Output. There it is, output. All right, and let's give these guys names. So I'm double clicking on the letters. If you double click on the box, it's gonna open this window. If you double click on the letters, you skip that step of opening the window. This will be my A. Let's do capital A to stay extra consistent. B and C. And then, oops, well, that's fine. And then you can do it this way too. Y is our output. Click OK. Great. Oh, that's because I clicked on output instead of pin name. All right. So now let's switch over to the Excel and look at that equation. So I'm looking at this guy right here. We're implementing B or A, B naught, A and B naught and C. So this midterm on the right, this is going to be a 3-input AND gate, and then we're having a 2-input OR gate. So we need to do a logical AND on A, not B, and C. Oh, and we need a NOT gate. We need to invert B to get NOT B. So let's switch back over here, and we will get our logic gates, and this window pops up. We're going to type in NOT. There is a NOT gate. We'll click OK. We're gonna put it not too close to B because we do need the regular. Oh, let's do this. Let's put it right there. Okay. Click on the mouse tool. There we go. And let's kind of snake a wire down there. And you see, I'm putting my mouse on the tip of the input until it changes the symbol, and then you get the crosshair, and you can click and drag down, and you get that elbow shape. You only get 1 turn per mouse drag. So I let go right here, and then I click the little tip right here until my crosshair changes, and I click and drag it out here, and it drags out a wire and it connects it. So now I have a connection to the NOT gate. And then additionally, we need the OR. We'll come back to the OR gate. Okay, so let's do the 3-input AND. So I'm gonna type in, and oh, maybe not caps, and 3. Yep, so I type in and 3. There it is. There's 3-input AND gate. And I will drop that down right here. And then our last piece of the logic gates is a 2-input OR gate. A 2-input OR gate. So I will type in OR 2. There it is, OR 2. And we'll drop it right at the exit. Okay, and then Let's go through and connect things up. So we got our not B, and we do have our C, and I don't like to cross over existing wires. Otherwise it starts getting messy. So you can see I'm just wiring up the connections. Okay, and then we need B connected right there. And then we need the output of this AND gate connected to the OR gate. Right there. And then those go to the output. Awesome. Oh, what happened there? Let's zoom in on that. Something went wrong. So I'm going to get the mouse tool, click that wire, hit delete. What is that? Let's move over. I don't know, something happened. Delete it. All right, and then we'll put that back in. Okay, good. Great. And we're done. We need to do our pin assignments, but let's verify this is what we wanted. I'm really hoping it's making sense to you, this Boolean algebra equation. Let's switch back over to the Excel sheet. We want B ORed with this big long min term of A and not B and C. So let's switch back over to Quartus. We have B ORed with not B and yes A and yes C. So not B simply means the opposite of B. Whatever B is, it's the opposite. Great, so we have derived this logic and we just slapped it on our diagram. Let's go ahead and save this. File save. Make sure you don't change the name. It's your top level design entity. This is important. Save it. And then we'll right click on analysis and we'll click start. Analysis and just the analysis and synthesis part is going to make sure that we made a valid circuit. It's not going to actually do the compile step yet. And then after this, we're going to do our pin assignments. We'll go ahead and compile it. We'll make our waveform, and then we're going to go ahead and program the board, and we will be on our way for the end of this video. How are we doing on time? Oh, okay. I think we're doing pretty solid on time. Okay. Now we are ready for pin assignments. And just like in the previous video, if you go to the repository that has the DE10 Nano web content and you go into assets, you're going to have this DE10 Nano schematic. This is where we're going to get our pin codes for our pin assignments. I'll minimize that for a second. We're going to go up to assignments and then pin planner. Yes, this is the guy. And we have all of our inputs and outputs here, and we need to assign a pin location. And in order to get the pin code, we need to look at the schematic. So I want A, B, and C to be on these switches. And in the previous video, I showed how you kind of look through this schematics PDF to find that information. But I believe it was on page 6 or 7. Let me see here. Oh yeah, page 6. I see my SW0, SW1, SW2, SW3. And let me switch over to the board view on the webcam. Let me verify that did switch the camera. Very nice, it did. I've got my glasses in the way. So here we are on the board, and the switches do have names. I cannot get that to show up on the picture. It's a low quality webcam. But if you look in between the Arduino header here and the switches all the way down on the plastic of the PCB board, there is some very, very tiny letters, and they read SW0 is the leftmost switch, SW1, SW2, SW3. Okay, so now you know which switch is what, and that's what we're connecting to. Let's go back to the desktop. So SW0 is code Y24. So on Quartus, we have Y24, enter. Next up is W24 for switch 1, W24. And next up is W21 for switch 2, W21, enter. And then lastly, our output. So our output is going to be on an LED, which I believe is on a previous page. I think it's some, yeah, here it is. Okay, I'm getting used to these schematics now. Let's do W15, our good old friend, LED 0. Why not? Actually, LED 0 is probably tired by now. Let's do V16 LED 2. We don't want LED 0 to get too tired. So V16, enter. And then per the My First FPGA write-up, it recommended switching these I/O standards to 3.3 LVTTL. I don't know what this means. I should do my research and understand what this is actually changing. But for consistency, because it works, I'm not even going to try and experiment with the other settings, because I don't know what they do. Okay, so everybody's set to 3.3 LVTTL. All these changes have been made immediately. Let's go ahead and close the pin assignment planner. Go back to Quartus. And let's get our waveform going. Our waveform is going to allow us to check. And actually, you know, it would make more sense if I would do the waveform before going through the work of the pin assignments. Because the waveform is supposed to tell you if you did things right, if this is really doing what you want it to do, before you go through all the work of getting it programmed to your board. So I think from here on out, I'm going to start doing the waveform before I start doing the pin assignments. But anyways, we're going to go to File, New, and then University Program VWF. Click OK. That opens up this window, and there is nothing here, but I'll right-click in the blank area under Name, go to Insert Node or Bus, go to Node Finder, list all the nodes, push the greater than sign to bring them all in. Click OK. Click OK. And here they all are. And then I like to do the clock. The clock is going to give you every single possible combination of each input signal. So we're going to do the count value. I'm going to bump this up to 100 nanoseconds. We're going to count in powers of 2. That is going to give us every single combination. So next time around, that'll be 200 nanoseconds. Very good. And the last one is going to be 400 nanoseconds. 400 nanoseconds, counting in binary. So we have a time when they're all 0, a time when A is 1, when B is 1, when A and B, when C is 1. We're counting in binary by doing powers of 2. This is binary. And then it all restarts over here. Great. So we're going to hit the little functional simulation. You could do timing. We're not actually running with any timing constraints, so we're going to do the functional simulation. It wants to save. You click yes, and then we'll click save, and then it's going to open. It's going to generate a test bench for you. Test benches is something I might get into in a future video. It's a more advanced topic, but definitely as you start getting into sequential circuits with registers and so on, you definitely want to be working with test benches to verify your design when things get more complicated. Okay, so I think what we need to do is we need to compare this waveform to our Excel truth table, our truth table on the Excel, because this is giving our truth table. So when they're all 0, so that is this guy. This is correct. Output is 0, so Y is 0. If A turns on and everybody else is 0, oh, I should do it the other way. Ah, too late. If A turns on and everybody else is 0, I didn't encode these to match the truth table. So A turns on, everybody else is 0, we should still be off. So this guy is good, and so on, right? A turns off and B is on and C is off. So that is this guy. We're looking good. Let me just blank out these guys really quickly. So we've only checked 3. Let's keep going. This is definitely important, doing this sort of thing of like actually proving that your design works. This is really important. Like, let's say your boss wants you to design a chip and they're going to order 10,000 of these things in an ASIC, and they're going to spend, I don't know, 25,000 for the fabrication or 50,000 for the fabrication. You're talking $50,000. Like, in order for you to get the economies of scale, you have to order a large quantity of chips, because it's very expensive to make one chip, but after they make the assembly line and they actually get the process going, the more chips you make, the cheaper each one becomes, and that's called economies of scale. It's a large upfront cost to get these things fabricated. So that is, again, another reason why you want to know how to do the waveform stuff. You want to know how to validate your design and really prove, yes, this thing is going to work. There's no bugs. There's no little kinks in here. There's no little flaws that are going to foil the whole design. Because once those chips are made, it is cemented in. The logic that you have implemented is permanent. You could get 10,000 chips that are absolutely useless because of one tiny mistake. And that is why you need to stress the importance of doing this verification. So don't think this is a waste of time. This is really serious. This is important if you're actually gonna take this far. So it seems mundane and boring, but it's trust me, this is what you got to do. Okay, so when A and B are off and C is on, B is off. A and B. Okay, that's this guy right here. That is looking good. Okay, when A is on, B is off, and C is on, that is our special case. That's this guy right here. We're looking good. When A is off, B is on, C is on, that is this guy. We're looking good. And when they're all on, our output's on. And again, this output, this is what I just decided were my requirements. I can go through and, let me finish what I'm doing first. Where's our last case? When we have A is on, that's this guy right here. A is on, B is on, C is off, it's 1. I wonder how I skipped that one. That's weird. All right, so just really quickly, these outputs, this was arbitrary. I can go through here. Let me put this back on clear, no fill. I can go through here and I can say, my requirement is this guy. And notice how this updates. And notice how my grouping is now incorrect. I have to do a different grouping. I have to do a grouping that's maybe more like this. And then that's going to change my equations. So my logic just changed. By changing one single output, my logic to implement this function has changed. All right, so I just want to illustrate that. I just did this arbitrarily. This deciding what goes here is up to you, or it's up to your project and what your project requires. That's where you get to punch in the numbers, and then you derive the logic that makes this truth table. That's, again, I just want to get that across too. That's the point of doing all this. Just want to make sure that's clear. Okay, cool. So our waveform is looking good. We are getting the green light to go ahead and program this FPGA and implement it on the board and see that it functions on the development kit. And then from then on, maybe you want to order some ASICs for this thing. Maybe not for this, but you get the idea. That's what this is all about. Okay, so we'll close that waveform. We did our pin assignment. We did our waveform. We are ready to compile. So I'm going to right click on compile and design, and I'll click start. And this will take a moment. So I'm going to pause the video while this goes. It'll take a couple minutes, and we'll be back when this is done compiling. Okay, we are back, and we have the green check marks on all of our, all of our compile process. I'm going to switch the camera over to the tabletop, and we need to get our board supplied with power. Make sure your micro SD card is removed from the slot. Leaving that in will erase your design after a few minutes, a few seconds. So go ahead and plug your power cable. And go ahead and plug in your USB cable to the USB port on the same side as the power cable. That J13, whatever. Plug it in. And we get that happy little connected device sound. Let's switch back to the desktop. I will go to Device Manager. I will verify that my device does have the USB. Excuse me. It does have the. Sorry. Resisting the urge to cough more. I don't know, something's in my throat. We want to make sure we have the JTAG cables entry in our device manager. Oh, to get to device manager, right click here, go to device manager. We have our USB blaster drivers installed. Go to, I forget, video 2? Yeah, video 2 for how to install the USB blaster drivers. Cool, so we are ready to program the board. We'll close this down. We'll go to Tools, and then we'll go to Programmer. And here is our programmer. We need to go up to Hardware. We need to make sure we have the DESOC selected, close, and we need to click Auto Detect. And then we're doing, I forget. Oh, we leave it default. We leave it default. I still kind of want to double check. So in the write-up, My First FPGA, this is a great resource. Link is in the description for where to get this guy. Let's go to the programming section. Yeah, it's the first one. Okay, good. I remembered correctly. Click OK, and we'll say yes. Yes. All right, and then we want to program the 5CSEBA6. That is our FPGA part. So we're going to select a file. So double click on None for file. Go to Output Files. Go to KMap Demos SOF. Open. And we'll check the box for Program and Configure. And we'll click Start. And it says Success. Let's switch over to the tabletop and see if this thing works. So, you know, I wonder if I can get the truth table to show up at the same time. I think I can do this. Let me move this over. So, sorry, I'm not changing anything. Let me get everything's fine. Let's get the window capture. Click OK. Let's bring in the Excel. Ah, there it is. Very nice. So we have our truth table on screen. This is exciting. Let's make this a little bit bigger. Let's cover the whole screen and we'll go that way a little bit. I like that. Okay, very nice. Okay, so, and then let me get my Excel over here. We're going to test this case first. So when all the switches are off, we should have the LED off. All the switches are down and the LED is off. Let's just skip to one where the LED will turn on. If we have B turning on, we should see the light turn on. So B is switch number 1, which is this middle left switch. It's the second switch from the right. Flip it on, and our LED turns on. That's great. Okay, so far we have validated that this works. This is exciting. I am very happy we get to actually see it in the physical world. It's not theoretical anymore. This is actually happening. Let's test this case. So if we turn on C, which is the third switch from the right, we should still have our LED light on. Okay, and let me see the camera. Is this close enough? Here, let me see if I can get this. I guess I can just, oh yeah, you can see. Yeah, you can see my switches. So that, I have something to point, oh, I do have something to point with. Okay, so this is my B switch, that guy right there, and that's my C switch. And the LED is still on. There is the LED over there. So we have just verified this one. Now, if we turn off B, we will be in this state. So C is on, A is off, and B is off. So if we turn off B, LED turns off. And C is on right now. C is on. And the LED turned off. Our output turned off. This is great. Now if we turn on A, nothing should happen. The LED should stay off. A, oh, we should turn off C. Turn off C. And then turn on A. And nothing happens. That is exactly what we want. But if we turn on A and we turn excuse me, and we turn on C, I need some water. I've been talking a lot in this video. Turn on C, it turns on. That is exactly our case right here. So we did not turn on B. The LED does follow B, but we did not turn on B. This is the special case where B is off, but A and C are on. You can see maybe there's some project you're doing where this is a practical thing. You want to always follow this signal except for one particular case where you want to follow a special case where A and C are on. You want to always follow the middle switch, this second switch from the right. You want to always follow that, except for one special case. Great, so let's just go through and verify all the other combinations. So if we turn off C, and A is on, but it doesn't care about A, it's looking for that special pattern when B is off. But if we turn on B, it'll follow B. So that is this case right here. We just did that. And if they're all on, it doesn't care if they're all on. It only cares if B is on. And that is true. It's following B. And if I turn off B, that is our special case. So we have just tested every single possible input on our switches here. And we saw that our logic that we specified, our logic here that we said we wanted for our project, this is happening. We've encoded this logic, and we didn't even have to think about it. We just followed a systematic way to get that equation, and yeah. So this is the conclusion for our video today, video number 4. Thank you so much for watching. Give me a like, give me a subscribe, all that good stuff. But yeah, feel free to join me in the next one. Thanks for watching. Okay, bye-bye.